So once again, a very good morning to all, and it's my pleasure to introduce Dr. Karthik Vaidyanathan, sir. He's an assistant professor at the Software Engineering Research Center, IIIT Hyderabad, where he is also associated with the leadership team of the Smart City Living Lab. He obtained his PhD degree from Gran Sasso Science Institute, Italy, and did his postdoc at the University of Alcala, Italy. And his main research interest lies in the intersection of software architecture and artificial intelligence, with a specific focus on building sustainable and self-adaptive software systems. His research focuses on how AI techniques can be leveraged to better architect self-adaptive systems, and further how to better define architecting practice for developing AI-enabled systems. As a part of his research activity, he serves as a reviewer, organizing committee members in various workshops, conferences, and journals, and he is also an editorial board member of IEEE Software. Sir, you are welcome, and the stage is yours.
Thank you. Great. So I think I'm audible. Yeah, very well audible. Awesome. So very good morning. It's an absolute honor and pleasure to be here. First of all, thanks to Dr. Mahendra for inviting me here, and also for all the arrangements for the wonderful stay, the food, and everything. So thank you so much, sir. And also to Shyamlal sir, who was there with us yesterday, and Gaurav, who was with us a few years back in IIIT Hyderabad. So it's wonderful to be here. I'm not going to talk anything about security. That's the first disclaimer, okay? But I will talk about many things that probably you could eventually use for security as well, right? So the focus of the talk is not going to be security, right? Probably many people are already doing that, right? But we are coming from a different angle where we are saying, hey, there is AI, there is software system, and software systems face a lot of problems. Why don't we use AI, right? So that's the crux of what I'm going to talk today at this point. But
excuse me, sir.
Yeah, sorry. Oh, should I speak from this or? So the crux of the talk is going to be about how to use AI for software systems in a particular way, which eventually can be extended to security aspect as well, right? So that's what I was telling the audience here. So without any further ado, I'll get started. But before I start, I just want to say something. If I just keep speaking, it'll be boring, right? Because I'm hearing only my noise. So if there are some questions in between, I'll be happy to answer that as well. So feel free to raise your hands or throw some thoughts, and we can have a discussion as well. It's not mandatory that I have to run through all the slides, okay? It's important that whatever I present is conveyed to you. That's the most important stuff, right? So what I wanted to say is, today there will be multiple sessions that we'll be doing. So I have my PhD student Rudro here with me. So he'll be doing a hands-on post this, and then we'll have one more session. So that's how we have structured the rest of it. So hopefully you don't get bored by seeing both of us throughout the next part of the day, right? So it's only us, yeah? Okay. Before I start, I want to start with this nice quote. Have you heard of Donald Knuth? How many of you heard of Donald Knuth? No one? Yeah, awesome. See, of course, he's one of the best computer scientists, right? We could say. He has contributed to many things. One of the contribution he is very relatable that you might know him for is the book of Art of Computer Programming, right? I mean, he wrote a lot of nice books on algorithms, right? That is even today being used for many competitive programming. Apart from that, he's also the person behind LaTeX and so on and so forth. So he said something very interesting, that he says that, in fact, what he would like to see is thousands of computer scientists let loose themselves out, think whatever they want. And he actually says that that's what advances the field, right? And I personally believe in this. So whatever I'm going to speak, some of it are a little far-fetched, which is potential, that's what research does, right? More frontier stuff. But some of this are something that we already know, right? So we'll try to mix it up, yeah? So, yeah, brief bio about myself. Already Dr. Mahendra very well introduced, so thanks for the nice introduction. So, I mean, apart from the fact that, I did my PhD, postdoc in Europe, whatever, the reason why I do this research at the intersection of software architecture and machine learning is primarily because I did one master's in software architecture, one in machine learning, and I ended up doing PhD in the intersection of both, right? Apart from that, I've also been in the industry for 6-7 years. So I understand how industry works. So whatever we try to do in research, we try to see how most of it could be relevant. I don't want to say all of it. Most of it could be relevant to the practice as well, right? So the research that we do are primarily in this side. One is machine learning for software architecture. So I'll talk about software architecture a bit today. which is how do you use machine learning for improving software engineering practices, for improving software architectural practices. So today's first talk is going to be, or even the second talk is primarily at that point. The second part is SA4ML, which is about how do you architect ML systems, right? Today, everyone are talking about, hey, let's build an AI system. But do we actually know what are the fundamentals to build an AI system? What are the challenges? Of course, security is a big challenge. How do you go about solving it, right? So that's the other side of it. But broadly, that's what the green color, we are very much interested in sustainability, which is whatever you do, be mindful of the environment, be mindful of the people who are building it, and be mindful of the society, and in general, the cost as well, right? So that's primarily the research area is all about. Fun facts, I'm just from God's own country, as we call, just next door to Mangalore, Kerala, right? We call God's own country, of course, that's a marketing gimmick, I believe, but it's really a beautiful state if you have never been there. I'm also a big time cricket fanatic and a movie buff, so if you are interested in talking about cricket and movie buff or movies, feel free to catch me during the lunch. Okay, so that's a bit about boring stuff about myself, and let's go to the actual part. So we all agree to this fact that we believe in this world of complex software systems, right? So there are a bunch of systems around us, right from a simple weather forecasting system that probably in the morning you'll say, okay, is it going to rain in Mangalore? To the fact that maybe you have a smartwatch that says, hey, you know what, I have a notification for you, your heart rate is dropping down, right? All the whatever crazy stuff. Then you have this kind of things like Alexas, you have this face recognition that is common in any mobile phone. And then you have the big ticket items like ChatGPT, right? It just came out and people said, okay, education is gone, whatever is gone, ChatGPT is going to rule us, whatever, right? People are scared about it. Then interestingly, this happened. Of course, if this was a presentation, not a PDF, I would have shown a small video of that. It's a robotic dance where the robots coordinate among themselves and they dance. It came from Boston Dynamics in 2019. It's one of the kind of a viral, at that time, Twitter, right, reel that went out and people started talking about it, right, where robots are kind of planning between them what to do. Of course, they are using AI and they are understanding how to dance, and it looked like a very nice dance, right? And on the other side, again, this was also a video, is a Tesla autopilot, right? Where the car autonomously drives through the streets of San Francisco, right? Just few days back, they also released another great version. They did a test drive without any person in that. In that, there is actually a driver who is sitting there, but Tesla recently did a test where there was no driver, it was just running, right? And they did it successfully. So what you see here is you can see levels of criticality of systems. On one side, you see a simple weather forecast system. Okay, if the weather prediction is wrong, you will just blame, okay, my app is wrong. Fine, no one really dies. Okay, you're fine with that. But if your Tesla car goes and crashes, it's a big problem, right? We don't want that to happen. If a robot doesn't dance well, you'll be like, okay, I wasted some money, maybe I'll improve it, right? Those are all fine. But as the complexity increases on this side, there is also a lot of threats that keeps coming up, right? Because of course we are sitting in a critical infrastructure workshop here. So I just want to touch upon that as well, right? So Tesla or any such things where the AI can have a potential impact on the safety of humans, that's something we need to be aware of, correct? So why I'm saying all this is because of the fact that if you want to think of building any of the system, right? The foundational aspect is going to be the architecture of this, right? Any of the systems, it may be the the Tesla autopilot. Just to give that fact, since we are talking about Teslas, it seems by 2030, most of your car's cost is going to be driven by the software, not by the hardware, right? I don't want to say anything to the people who are working on the hardware. What I'm trying to say is software is actually driving the economy in that sense, right? Of the autonomous vehicles and so on. It seems when I say 2030, I'm not overestimating. I think I'm underestimating because it's already, if you look at today, if you want to buy a Tata car, right? That's what I bought recently. And if you compare between models, the only difference is the amount of features in software, not hardware. They are same doors, same steering wheel, everything is the same. Just the apps changes, the software changes, and the cost changes, correct? So the foundations of all this is software architecture, right? So I just want to touch upon briefly to this and I'll come back to why these are the problems I was talking about. So the foundation of all this is software architecture. The moment when I say software architecture, will be like, what is it all about, right? Any idea what is software architecture? You saw an image there. Yeah? Systematic planning and execution of what we, yeah, fair enough. It goes in line, yeah, fair. What else? It's just planning. So you just plan. What else? It's a design, fair. Okay, it's some kind of a design, right? Design of a software that you want to build, which you plan and you come up with a nice design. But is it all that? What else? With some analysis, right? You don't randomly come with something, you make some kind of decisions, you are saying, okay, this is because of that, that is because of this, and finally you end up building a nice architecture, right? So let's take an analogy. Of course, this is a very simple analogy here, right? I mean, what will you do if you want to build a house, right? You won't directly say, oh, let me start putting the bricks. Right? That's not how it works. And if there are civil engineers sitting in the room, they will kill me saying that, hey, what are you saying here, right? Because the whole process involves a bunch of interactions. You first go, you'll say, hey, I want a nice house, these are my requirements, and some nice civil engineer or architect will come up with a nice plan, and based on the plan, you'll say, okay, let me start, putting together stuff. Even then, you're not going to put the bricks. You will ask the people if you are okay with this, right? You will probably show the design to your, whoever is planning to build. When I was constructing, I was seeing this plan, I was able to understand something because I did basics of civil engineering, right? The CAD design or whatever. But my mom was like, what is this? Right? Because she doesn't have the civil background, she has a stats background. She was like, what is this whole thing about? What are you trying to say with this? Right? And I told my civil engineer, hey, this doesn't work, can you give me a different view of this? Right? And what did he did? He probably created a nice 3D plan of the house and said, hey, this is probably how I want to build the house. And then we say suggestions. Once everything is finalized, you start building the actual house. Only difference, with this is very similar to what we do in software architecture. The only difference is, in a house, once you build it, you cannot break it. But in software, you can always break it. But it also comes with a cost, right? It's not that, oh, there is a software running, right? There is a Tesla autopilot that is running, let me, dynamically change it, right? It's tricky. That's what we are going to talk about today, right? How we can do that. Okay, so essentially, if you go by the definition of software architecture for people who are interested, because something that we are going to do in the afternoon also has relevance to this, is that it's a bunch of, if you come up with a bunch of requirements, you come up with a bunch of requirements, that requirements drive your architecture. This architecture eventually translates to the low-level design. This is what actually you program and you deploy the system. And this is a continuous process. This is not a waterfall process like back in the 90s. You're continuously doing this. So your software is constantly evolving. This is not like a one-time process. So essentially, if you want to look at the definition, it just says this. It's about a bunch of components, which is what are the key components I want to use in order to build my software system. Like, okay, I want these rooms, right, in my house. And now how the rooms are connected to each other. Probably they have a nice floor plan through which they are connected. So similarly, what are the technical components or what are the software components I want to talk about? How are they connected to each other? And then the reasoning behind it. Why did I do this? This is very important, right? Because after 20 years, you want to go back and change the software. Today, companies are struggling with that, right? If you go to Infosys and talk, say that, hey, what is the biggest business for you? They will say maintenance, right? Because maintaining the software takes a lot of effort. Why it is effort? Because no one knows why a particular system was built in a particular way, right? So that decisions you need to capture. So if you capture all this, then you say, okay, you have a nice software architecture for the system. But then what is a big problem, right? Big problem is we said that there are multiple ways to do this. There's not a single way to do this, right? Over the years, we have changed the way in which we build softwares. It started in 1990s. So what I have here in front of you is an example of how an e-commerce would have been built if you are building it in 1990s versus 2000s versus later 2010. The same e-commerce system like your Amazon, Flipkart, whatever you like, or even the Swiggy, Zomatos, right? So if I am talking about 1990s, I'll probably build it as a monolithic system where I'll have everything built as one large piece of code, right? Probably even today we write projects like that. Everything is one script.py. Now you figure out how everything works. We are not going to tell you what is separated here. Right? That was the whole idea where everything is sitting in one piece of code and you're going to deploy it as it is. But then later people figured out, hey, in this, there are many pieces that I want to reuse. So if I'm putting them together as a glue, I'm not able to reuse them. So they said, what can I do about this? So that is when in 2000s, the concept of service-oriented architecture came. So the same e-commerce system, what you do is you build as reusable services. When I say service, just to give a simple example, it's like a Python Flask. How many of you have written Python Flask? Or a Spring Boot, some web service, any web service, right? So it's a web service. So it's an independent web service, and this web service is like a plug and play module, right? I can pick it out and I can plug it in, right? So this is different from this. Now, but here no one defined how big this service should be or how small the service should be. And moreover, there were a lot of asks from the industry. I'm not going into that details of the story. So 2010 what they said is, okay, let's do it more fine-grained. Instead of saying everything is a service, let's say that every small functionality becomes one service, right? So if I say I am building an e-commerce system and I want to do authorization, okay, authorization service. If I want to add carts, add items to my cart, okay, item add or to the cart service, right? So you build all these independent services and every service will have its own database, right? This is a foundational concept of a microservice system and they all interact with each other through lightweight protocols. Here it was not lightweight protocol, it was all tied together with something called enterprise service bus. These are details, you don't have to bother about that, okay? And now in 20s, you are talking about serverless systems, connected systems, and blah, 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 right? Now they said, can I break this down further into independent units? That's where we are talking about this AWS Lambdas, GCP function, Azure function, and so on, right? So anyway, but the biggest challenge is systems fail and they go down. Now you say, okay, Karthik, software architecture has evolved over the years. You know, people have done tremendous amount of research, but big challenge is systems still fail and they go down. So how do you take that into account? I mean, systems are still under security threat, right? After building so much nicely, you still have DDoS attack, right? Your intrusion coming into your system, right? So how do you take that into account? And because of that, what happens, right? For example, see, Amazon Web Services had an overwhelmed network. I mean, a lot of networks started connecting. It was just a very basic DNS issue, right? But you cannot blame Amazon because it's a large organization. Someone did something with the DNS and it collapsed. It resulted in billions of dollars loss because many people are relying on AWS. It's the largest cloud provider today, right? Similarly, Meta, right? It was very interesting, very similar problem. So Meta completely went down, right? So Meta goes down means today what? WhatsApp goes down, Instagram goes down, Facebook goes down. I don't know what else will go down in future because they are buying so many things, right? So all this went down. People started tweeting, hey, you know, Facebook went down, what do we do, right? Think of something like a CrowdStrike. CrowdStrike is one of the biggest issues that happened, right? There was a blue screen. How many of you have seen this blue screen in Windows? Yeah, we are all familiar, right? This entire blue screen happened across the world. Most of this, at least 10% of the people who are, you know, users of CrowdStrike, which is like a security company, they were, you know, so they released a patch that actually created the problem and flight stopped. People couldn't even move. See the impact of software. A software fails, you cannot travel. That's where we are today. Okay, this is just to tell you where we are with respect to, you know, how much software has actually intruded into our daily life today, right? If I take off the phone for some time, we don't know. For example, recently there was a discussion where they said every student, in order to make themselves meditative, can you say that you take all your devices away during the class so that you try to attend the class? And if you are successful, it means that you have a meditation therapy. I feel that it will go the other way. They will nicely sit and also close their eyes. Right? So because, see, the attention span has reduced. We are not blaming the students, right? The attention span has reduced. So what I'm essentially trying to say is, even in spite of all these developments, software systems go down. So how do you take that into account? Which brings us to the fact that there are a lot of uncertainties in the system, right? Why this is happening? Because you never know. Suddenly someone might say something, suddenly you might get a security threat, suddenly number of users who are using the system might increase. So Flipkart would have thought that only 10,000 users will use it, but suddenly 1 lakh users use the system just collapsed because it was not designed to handle it, correct? So these are called uncertainties because you don't know that these are going to happen. When you design the software, when you create the architecture, as some of you said, you don't know that this is exactly what is going to happen. You can only plan for certain scenarios. Here, for example, I am going from NIT Surathkal to airport. I know that the road, the traffic conditions are like this, it will take this much time. What if suddenly, some block happened? It's not something you can plan for. You cannot plan for, if the block happens, so I'll start 5 hours early. That doesn't make sense, correct? So these are runtime. When the things are happening, many uncertainties are happening, and now how do you react to it? So that is what we want to bring in, right? So this kind of impact the system's quality of service. When I say quality of service, suddenly a security threat comes, your system goes down, your availability is down. Now your system is not accessible, right? So what can you do about this? So that is where we want to introduce this notion, right? I don't know if you have heard of this concept of something called self-adaptation, right? Where the idea is, what if systems could adapt themselves? Right? We humans have this tendency, right? For example, imagine that it's really pouring, right? It's raining. So you'll be like, okay, how do I go out? I don't have an umbrella. Maybe you'll search for an umbrella, you don't have it, or you might just walk wet drenched. Fine, that day you will enjoy. But next day, or next time when you're there, you'll be like, this place rains, man. Let me carry an umbrella with me. You won't repeat that mistake because in our memory, we have adapted saying that, okay, next time this happens, I need to know what to do. Okay, so similarly, what if softwares could do that? Right? What if software is suddenly encountering a failure and the software figures out, hey, this is the failure, I've not seen it before, but let me see what I can do. and autonomously come with a solution without human intervention or with minimal human intervention, I'll come up with a solution and I'll fix myself, right? And I'm back again. So this is the whole concept. This could be a security threat as well. It could be with anything, but if the system goes down, if there is an effect on the performance of the system, can the system come back by itself, right? So this is the whole concept of self-adaptation. So this was actually framed in a very nice paper, if you are interested, Vision of Autonomic Computing in 2003 by IBM folks. They came up with this very interesting paper, right? They said that what if systems could adapt like human cells? See, even if you get a small injury, you're not going to put turmeric, I mean, it's very rare, right? You're not going to stitch it, right? Small injury, you know that the skin knows how to heal itself. You'll just leave it open. People will say, hey, just leave it open, it'll be fine. Because our cells have an ability to self-heal, right? You don't have to teach them because they have it in their, whatever, biological memory or whatever. It knows how to handle itself. Similarly, what if systems knows how to handle itself, right? That's why I said minimal human intervention, because if there are major problems, you might need some kind of human intervention. But in most of the cases, systems can automatically fix by itself. So to this, what they did is they also created a very nice framework called a MakeK, right? So what they do is anything that you want to manage, it could be a software system, it could be anything. You can take any real life example also. If you want to see what is happening to the system, what you do is you constantly monitor, right? So for example, if someone has put you on a guard duty and you want to say that, okay, if something is happening to a room, what do? You constantly keep monitoring, right? Monitor, and then what happens? Imagine that someone randomly comes in, you will analyze. Okay, is this person allowed to come in this room, right? If this person is not allowed, then you will be, okay, what should be the action I should take? Should I ask him to go out? Should I ask him to enter the details, right? And finally, I have to execute that, saying that, okay, you're thrown out or you're permitted in, right? So these are final part, which is the execute. So similarly, we are saying a software system is running, you constantly monitor the software, you understand what is happening in the software, you plan if there is some kind of an uncertainty that has happened, what needs to be done, and you execute the plan back to the system. So if I can continuously keep doing this, right, then what I'm essentially saying is your system does not need any human intervention, okay, it can autonomously function by itself. Okay, I'm not saying that your jobs will be gone. What I'm essentially trying to say is that this is potential possibility that was given in 2003 itself. But it took a lot of challenge, because it's not very easy to realize such a system, right? Back in 2003, someone had a vision to talk about this, but it's not very easy to realize. So I'll just talk about some conceptual models. So the question you can ask, how do we go about doing it? One of the conceptual model is any running software system is called as a managed system, right? So this is a running software system. It will have some kind of goals. Now, the goals, you can think of the fact that, okay, my system should not go down. Even if my system goes down, it should be able to come back by a certain time. It should be able to serve thousands of users. The response time or latency might be minimal. So all these are different goals. And your system is interacting with an environment, right? When I say, oh, what happened here? Oh, it's a touch screen. Oh my God. How do I solve this? Oh, great. Yeah, thanks. Yeah, so I wish it was adaptive as well, yeah. Oh, I think we'll just have to do a Control L, because otherwise this is. Okay, cool. So what essentially the idea is, you have a running software system and you have a managing system. So the running software system has a lot of goals, and it is going to interact with the environment. Now, what is an environment? Environment is a place where you deploy the software. It could be your server. It could be the network that is associated. It could be the users who are using. So anything that is external to the software is considered as an environment. Or anything to which the software is interacting with, you can consider it as an environment, right? And then to that, you add a managing system, which is the person who is responsible for adapting, right? This managing system is going to constantly monitor both the environment as well as the running software system, and it is going to decide what needs to be done so that it does not go down, right? So this is essentially the idea. Yeah, there are multiple ways by which you can do this. So for example, self-adaptation mechanisms in code. If you're writing a program, you will write exceptions, right? You'll say that, okay, if there is a zero number, you will say that there is a divide by zero that is going to happen, so you don't permit the user to enter zero, correct? If you want to do A by B and someone is entering B as zero, you will raise an exception. So this is simple things that are learned at the code level. But at the system level, what can you do, right? If the system is under attack, what can you do, right? Can you autonomously make the system realize that, hey, you are under attack, do something about it instead of going down, right? So this is all we are trying to achieve, okay? So there are multiple frameworks that has been built over. Just go over some of the frameworks so that you have an idea, or if you want some pointers to maybe go later and do some deep research on it. There is a framework called Rainbow that was proposed by some folks in Carnegie Mellon, right? So it was a very nice framework. I mean, again, I don't want to get into the details, but what they said is, same thing, you can consider a software system, it's a system layer, and the system layer has a bunch of effectors. So effectors are mechanisms through which you can invoke something to the running software system. If I want to talk in IoT terms, you can think of it like an actuator, okay? Something through which I can actuate something on the system, okay? And then there is something called probes. Probes are mechanisms through which I can understand what is happening within my system. So you will say, okay, Karthik, what if the system does not provide anything? Then you're gone. I mean, you have to rebuild the system, right? So there should be some level where the system is going to provide you some details on what is happening within the system. If that is there, then you can do all this, whatever nice things you can do, and then you can come back. Now, what does Rainbow propose? What Rainbow says is, you have a bunch of probes, you have a bunch of effectors, and there is an API, right, which will allow you to execute something on the real system. What it says is, it is attaching an architectural layer. In the architectural layer, it has a model of the system. So when I say a model of a system, imagine that you want to build a car, right? Most of the time, car is not built just like that, right? They will create a nice model of the car. They will simulate some conditions of the car in the model. And once everything is fine, they will actually start building the car, right? So kind of the analysis that you do in your design. Similarly, what you do is you create the model of the system itself, the software system itself. There are ways to create it. I'm not going into the details of it. This model is kept in some kind of a memory. So whenever something happens to the real system, what you do is you check it in the model if there are some problems within the model here, and you see what could be the fix by simulating the model in different directions, and you check if this can solve the problem. If it can solve the problem, you apply to the real system. So it's more like a model-based approach, right? You abstract out everything, you see what is happening in the system, you supply to a model, the model will tell you whether it is good or bad and what kind of decision you can take, and it can apply it back to the system. When I'm talking model, I'm not talking about AI model, okay? I'm just talking about a blueprint, if you want to think like that. Blueprint of the real running software system, okay? Okay, any questions? Okay, so I'll just give a simple example to make this more clear. So this is a very simple example called Swim. It's a classic example in self-adaptation, right? It's a kind of a toy system that you can actually play around with. Okay, you can download this, you can play around with this. So Swim is like a web infrastructure simulator. Now what Swim has, of course you have a web browser that users are using. What it tries to simulate is users are using the web. Okay, now if users have to use the web, somebody has to serve the web page, right? When you type google.com, someone is showing the HTML page of Google, the Google server is handling it. Okay, now imagine that suddenly large number of people come in. Okay, now what you might have to do as Google is you need to increase the number of servers so that so many people can be served. You know, Google has hectares of server farms. That's why it is able to handle so much of load, right? Otherwise it's gone. You cannot operate Google with one server, correct? If you want to really give a try, take a laptop, build a web service, hit it with like 20,000 requests per second. It will crash, depending on the RAM, okay? So now I'll have to add the web server. But every time I add a server, what is the problem? If I add some server, what will happen? Great man, good point. Thank you so much. Yeah, your cost will increase because you cannot randomly add some servers, because if you add a server, you are going to increase the cost. But what is the benefit of adding a server? Huh? Yes, or the response time to the user is going to be less. The user is going to be served fast. Okay, so now you have a trade-off. On one side, whether I should increase my cost. On the other side, should I, give service to my user, right? There is also something in between that Swim provides, which is, I'll show you a web page, but I'll reduce the graphical content in my web page, right? In this way, I'll still show you something, but you won't get the optimal stuff, right? It's like you go to a nice shop, apples are available at a reduced cost, but the apples have some problems, right? If you're okay, you can buy it and cut it and eat. And essentially, right? That's what here we are trying to do. Yeah, factory outlet, yes, correct. You go to a factory outlet, small defects, if you are okay, you can take some thread will be gone, something will be there, yeah? So, you can do that. Now the question is, how do you balance between all this? Because the better I serve my user, the user is also going to give me something. What is that? You talked about the cost, you talked about latency, but there is also one thing, the user is using the system, which means what? Huh? Why should someone use, what is the benefit of Amazon if people use their system?
User will pay.
Yes. So there is a revenue that is coming up, right? So on one side I have revenue, on one side I have cost, on one side I have to optimize response time and have a bunch of methods to do that. I can add server, I can remove servers, I can change my graphical content. So what Swim says is, can you create a self-adaptive mechanism where if I dynamically change, it's a very simple load balancer example, but just to give you an idea of self-adaptation, can you create an algorithm that will decide when to add a server, when to remove a server, when to increase the graphical content, when to reduce the graphical content based on the number of users, looking at my cost, looking at my revenue in such a way that I can optimize all of this. It's a multi-objective optimization. It's very hard, right? So how do you do that? Correct? So there are a bunch of ways. If you go to Swim, they provide a set of mechanisms by which you could do that. We could also use AI to do that. You could use many other approaches to do that. So we will talk about what we did with generative AI in this example in the later half of the session, maybe in the afternoon. But what Swim does is, Swim does something called a reactive approach, which is whenever it sees that it has always a goal. The goal of Swim is to ensure that the response time for the user does not go very high. Because the moment response time goes high, a user is going to say, this is a bad website, why should I use this? Right? If you go to Amazon and wait for 20 minutes to pay, for one time you'll be okay, two times you'll be okay, after that you'll be like, forget it. IRCTC, we don't have a choice. Okay? But you'll be like, what will I do? Right? So in this case, the problem is you don't want the response time to go very high. So how do I go about doing this? So what Swim says is every time it goes up in a reactive way, which is as soon as it goes up, do something about it. Maybe I'll add a server, right? Or I will reduce my dimmer. Dimmer is actually the value that controls the graphical content, okay? And so on one side you see the number of requests, which is how many users are using your system. On the other side you see the response time. Every time my response time goes up, what I'll do is I'll immediately act. So this is called a reactive adaptation, which is whenever I have something, I perform an adaptation, right? And then you have a utility. So utility essentially tells you how well did you perform. So it's a combination of scores, right? It's kind of a linear combination of all the scores where it says, it's not linear, it's piecewise linear. Yeah, it's a piecewise linear function where it kind of combines all the scores and says how good was your adaptation strategy, right? And if it is high, it means that essentially you did very well. So the traditional Swim offers a utility of 3,500, which is the approach or the algorithm they have used. Now, if you want to come up with a better adaptation algorithm, you can implement it on Swim and show that it can defeat the benchmark. Great. So if you have some time, please go and try it. It's very easy to use. Okay. So, but the problem, I stressed on this, but I just want to highlight some of the challenges in self-adaptation. One is the reactive nature of adaptation. So every time I want to perform an adaptation, I decide, what needs to be triggered. But this is not very good idea because reactive is great. But sometimes we tell to people also, right, be more proactive, right? Because you want the person to also think 2 miles ahead or 2 steps ahead so the system does not go down. See, the other day, one person was telling me from a big company that if their system even goes down for point some seconds, they are going to use some millions of dollars. So they cannot even afford for the system to go down that much, right? So, which means reactive is great, but reactive only gets triggered when something has happened. Oh, my system went down, let me think what to do. But system is already down, correct? So can we do proactive? Second part is systems adapt, but they do not learn, right? This is where I want to clearly make a distinction between adaptation and learning. See, adaptation is more an instantaneous process, right? I have something, I do something, great, I adapt it. But learning is when next time the same situation happens, I already have my past knowledge on what I adapted, how I adapted. Based on that, I will do a better adaptation this time. So I have some memory that I'm using, based on that I'm improving. I'm not staying, so it's not like if I'm present with the same condition, I won't probably take the same action. Humans do that, right? If every day I put you in the same scenario, the way in which you react to that scenario will be different because you will learn every time. First time you'll go for an interview, probably you'll fail. Next time you go for an interview, you won't go through the same problem, right? You will be like, okay, let me do something different. You have adapted. And for the next interview, you have taken all these 2 learnings and you are further improving, right? So how do you ensure that the systems learns, they don't just adapt? So with every adaptation, can I contribute something to the learning? And finally, learning is also a dangerous process, right? For example, you learn, but who tells you that learning is correct? right? In our case, when we learn something, we go and write an exam. Someone is going to say, okay, you learned well. Okay, whether the exams are the best way or not, we'll keep it aside, right? But there is some way by which you can be measured, and someone is quantifying you, saying that, okay, you are this much good or you are that much good, and so on. So how do you provide this assurance to the learning itself? Okay, these are the three challenges that we are going to do with, and of course, I'm not going to talk about this. So essentially, the idea what we thought when we saw these challenges, since systems have to learn, not just adapt, how do we constantly learn? How do you provide guarantees to learning, and how do you make it proactive? So that's when we started asking this question some years back, can we use machine learning, right? Again, I'm using machine learning in a very clear way. I'm not talking generally AI learning, because at that time we were talking only machine learning, right? Of course, I hope it's very clear, the distinction, yeah? So, of course, there are very nice definition given by multiple people, so I'm not going to go about this. I know this crowd is already into too much of machine learning, but yeah, these are the personal favorite definitions for me, one by Tom Mitchell and one by Arthur Samuel. I'm more fan of the definition given by Tom Mitchell, because what I thought is, here he says with respect to a computer program, right, it's set to learn from an experience E with respect to some class of task T and the performance measure P. Similarly, I thought, what if how do you say the systems can autonomously learn? You can say systems can autonomously learn if the system with experience E, right, can improve its performance for a given task over time. The system itself can learn, right, not just a program. So the program can be an enabler for the system to learn. So that's how we started thinking about solving this problem, right? So it actually came from down the definition of machine learning itself. So what is the overall goal that we are talking about? So the overall goal we are talking about is, given a software system, it could be any system, right? I've just given an image of a nice IoT system or whatever, right? Given a system, can I come up with an approach that constantly understands what is happening in the system? I have a bunch of goals that I have to maintain. For example, I might have goals related to energy, I might have goals related to security, I might have goals related to cost, performance, whatever, blah, 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 right? There is a bunch of goals. Now, can I come up with a mechanism that constantly adapts the system, right? Gets feedback, learn from the feedback, generate more actions, verify if the actions are correct, apply it back to the system, and keep continuously doing this in such a way that over time my system also improves and the system knows how to pretty much handle itself. It's the thought that in fact, we wrote a nice article on this. I'll probably share it at the end. So I'll give a small case study. I think Gaurav would have seen this case study. So this is a case study just to give an example of how this could be put in action, right? I'll give some research results from this study as well. Again, whatever I'm presenting here is purely our research, yeah? So don't ask me which textbook has it. There is a bunch of papers where we have written this, so you can read it. I'm citing it everywhere, yeah? Okay, so NDR case study, it stands for, since I was in Italy doing my PhD, I was in the city of L'Aquila, right? L'Aquila stands for the eagle. Right? It's called the Eagle City. It's also pretty high. Yeah. So in terms of the distance from the sea level. So what happens is this city hosts something called Notte di Ricercatori in Italian, which means researchers' night. Okay, it's an event where all the public come to the center and there is a presentation of all the scientific activities done by the research students, by the faculties. So everyone from the university will go there and present their work to the common public. So it's like a scientific exhibition. And there will be also dance performances, there will be songs, everything, right? Food, of course. So what happens is this city is a very small city and it gets crowded. When I say crowded, the numbers are significantly, or I don't know, 110 times, 120 times, whatever less than what we see in India, okay? It's just 25,000, 30,000 they call crowding. Okay, we cannot compare with Indian standards. 20,000 is nothing. Probably if I go to Hyderabad center, I'll find 20,000 people. Yeah. So, but all these people coming together, the city will become congested because the city was not designed for such a crowd. What happens is people also come with the cars, right? So Europe, yeah, things are better organized. That doesn't mean that everything is fine. Yeah. So people come with the cars and everything is, congested. So you need to come up with mechanisms by which you can redirect them to places. Right? And you don't want them to fill up the venues. So for example, if you have a room like this and there is a performance going on, right? And you have capacity of, I don't know how many, maybe 70, 60, whatever, you don't want it to be overflowed because people will be standing. So how do you ensure that this is handled? So essentially they asked us, they came to the university and said, can you guys build a crowd management system? Okay, so we built a nice app which tells you, when is an event, how many slots are available, which venues you can go. If you select a venue, it will say what is the best parking lot I could suggest to you to. So all this kind of suggestions are possible with this application. But we had a lot of challenges, right? So when we thought of doing this initially, we said, in order to do this, we have to get the real-time information of how many people are coming in, how many are coming in, which venue is free, which venue is available. So all this information you should be able to capture. So we created a very high-level initial design where we said, let's break this down into two systems. One is a parking control system, one is a venue control system. Parking control system is going to ensure that all the parking lots are controlled in the best way possible so that people don't dynamically put the cars wherever they want. On the other side, you want a control on how many people are in a particular venue so there is no crowding. Okay? So for this, we employed cameras, we had people counters. So every time you enter into a venue, you have a barcode reader that reads you and you are in. And whenever you go out, you take a different exit route and there will be a people counter. So it just keeps counting. Because when you are entering, we want to be sure that you are actually the person who is supposed to enter. But when you are exiting, it's fine anyway, you exit. Yeah. Similarly, for parking, whenever a car comes, we have a mat. That's a sensor that will just increase the count by 1. So that we know whenever a car is coming into a parking lot. Right. So this is the basic stuff we had. But we had a lot of challenges in this, right? Of course, one of the constraints is 35,000 visitors. So the number of users who are using the system is very high. Then we had observations like late hours are more crowded than early hours. So we did a study on the users, the patterns and all those things. Yeah, I'm not going into the details. And there is a limited availability of parking lots. Even more interesting thing is you cannot put sensors randomly wherever you want because it's a city center. In most of the places you don't have power sockets, so they are battery powered, right? And you also want to provide accurate information to the people, right? So how do you combine all this? One of the biggest challenges for us was the fact that they are battery powered. Of course, this is an extrapolated stuff from that. We said that if they are battery powered, right? If they have this challenge of accurate information, can we sort of think of a dynamic adaptation mechanism where the system itself can adapt in such a way that the battery is optimized? At the same time, the users are able to get the real-time information in the best way possible, right? So the first thing that we had to do was we wanted to move from reactive to proactive, because if we do a reactive adaptation here, I can say I don't want my system to consume or my sensor to consume more than this much battery. So whenever it consumes that much battery, I will do an adaptation. That is reactive. I don't want to do that. Right? I wanted to move towards proactive. So what we said is, can we generate forecasts? So this is what we started with, right? We said the forecast, right? We constantly monitor the system and we predict how much battery will be left, how much performance loss will happen if the system is operating in a particular way. And based on that, can we come up with adaptation? So it was a basic change, just moving from reactive to proactive. An interesting thing about this quality of service data, when I say quality of service data, any data in terms of performance data, your response time, throughput, CPU utilization, they all have a very temporal nature, which means for every instance of time, you have a value, right? So it's essentially a sequential data. Correct? So if you have a continuous sequence of data, we said, and it's a temporal nature, we said, why don't we live with something like time series forecasting? Because it can forecast, predict the expected quality of service attributes. Based on that, I can make a decision. So we came to an elaborate approach where we said, okay, now we will force fit, or on top of the existing system, we'll put a MAPK loop. Now this MAPK loop, what does it do? It will constantly monitor the quality of service data of the IoT system, which is how much battery the sensors have, how much packets they are sending. All this information is captured, and then it is sent to an analyze loop where you have a data processor and a predictor. So predictor is nothing but an AI model, of course an DL model here, deep learning model, which is a time series forecasting model which predicts the expected quality of service. And based on this prediction, I go to a decision maker which decides what needs to be done. Okay, I'll go to the decision part later, but our initial focus was to build this. So if you see these gray boxes, our initial work that we have published here was only focusing on this three things. One is monitor, one is analyze, and knowledge. So knowledge is the place where you store all the machine learning models, the quality of service goals, and the configuration. Now when I say machine learning models, for every quality of service attribute, you might want to build a different model, right? Because one model may not be able to predict every quality of service. This is something we have tested, right? So all these models need to be stored, and the models need to be updated periodically. That's why we have a machine learning engine which periodically takes the data, updates the model, and keeps putting the model back to the knowledge, right? So of course, this is a machine learning engine, simple stuff. There is a data store, feature extractor which builds it, and we have a trained LSTM network. So we use long short-term memory network. Again, I don't want to get into the details, but it's a Probably it's a class of RNN. I don't know how many of you heard of LSTMs? Okay, some people. Yeah, just to give a simple idea, it just gives you a forecast of the expected data after some point. So the good thing is recurrent neural network can be used for sequence prediction problems. But one of the fundamental issue that a traditional RNN has is it cannot remember so many past observations so that it can predict the future accurately. Right? For example, if I tell you the weather forecast, weather information of the past 20 days, you can predict the 21st day better, right? But if you have to store that much information about the relation between 20 days, you need some mechanism to do that, which RNN didn't have, a traditional RNN didn't have. So LSTMs came up. This was 1997 work, okay? But it took some time to really have the computational power to reach where we are, okay? Okay, so that was fine. So we did that initially and we said, okay, this is still proactive, but can we do more than this, right? So the next step for us was, we can perform prediction. But even the previous case, here what we were doing is, based on the prediction, we were just making a decision. But next time I'm going to say in the similar situation, I'll again go through the same process to make a decision. But I don't want that, because the whole point we have been trying to talk is, how do I dynamically improve as well, not just adapt? How do I learn, right? So we wanted to induce that into my system. So we said, can we further do something more? So instead of just generating the forecast, identifying a plan and executing, can we say, I generate a forecast, I identify a plan, right, I execute it, but next time if I see a similar situation, I go back and understand what happened previously. So for example, I am in this room, right, I did a mistake now. Let's say I just flipped over. Oh, I hope that does not happen. Yeah, I flipped over. So next time I'm standing here, I would have been like, okay, I don't want to flip over because I have my previous memory. So how do you capture that? That's essentially the question was. Any machine learning technique that you think can be used for this? Yes, right? So we just went there, we said, what can we do? Can we do a RL based approach here, where can we, based on the feedbacks, can I improve, right? So essentially the idea we talked about was, so now coming to the plan itself, right? So what can we do? So if you talk about a traditional IoT system or any cyber physical system for that matter, you can go with an edge based approach where everything happens on the edge nodes, right? So edge node could be your laptop, your mobile phone, and you can put your AI models, whatever you want there. But the problem with the edge is it's very energy consuming because it drains a lot of battery. But the good thing is the latency is very low because you quickly get everything from the edge itself. Other thing that you can do is you can put everything to the cloud. So edge will keep sending data to the cloud and it will come back. The good thing here is battery is saved, but it's going to be taking time. And it's also costly, definitely, because you're putting everything in cloud. Or you could also put something in between, a fog, saying that, okay, everything in NIT Surathkal goes to a server in NIT Surathkal, everything in NIT Warangal goes to a server in NIT Warangal, and together they will learn something. But this has a higher setup cost. So we said, but everyone has their own advantages and disadvantages, right? So we said, what if we could dynamically adapt by saying, I'll use edge for now, I'll go to cloud now, I'll go to fog now, I'll keep switching between them. I have all the infrastructure, yes, that's a trade-off you pay. But the good thing is, my system will provide guarantees on, if edge is not working, I'll probably rely on cloud. If cloud is not working, I'll probably rely on fog. So I have this option to dynamically switch between them. Of course, there is a consistency challenge. I'll talk a bit about that. So of course, we used at that point was, we in order to try this, we use a basic idea. It's not a big RL based approach. At this point, if you talk about, all this PPOs and everything, I'm not even talking anything closer to that, not a deep RL. I'm just talking about a simple RL. It was a classical Q-learning because now the amount of actions you want to perform is only 3, right? For people who know RL here. So RL, the idea is, we wanted to use something like a model-free learning technique because we didn't want to store any information as such, but we want the system to just learn as it goes. We don't want the system to take any prior assumptions. So what is model-free? I don't have any idea of the model. So what is model here? Model is essentially the model of the environment itself. So for example, let's imagine that I'm inside this room. I don't know the map of this room. My eyes are closed, or of course the room is dark and I need to navigate this room, right? I don't have the model of the room. What I'll do, I'll straight walk, I'll hit the wall. I'll understand that, okay, this is not actually the way. Let me try to go the other side. And always the actions I have is I can turn right, turn left, right, move backward, move forward, right? Of course, humans can also move sidewards as well, right? Whatever, right? So you can do all the actions, but the goal is to navigate the space without having the map of this. Maybe if I keep doing that multiple times, over time I'll know, okay, this is where the wall is at this much distance. So if I immediately sense it, maybe I will go to the other side. This is how typically, robots used to learn. Today there are more advanced mechanisms. So we said, can we do this, right? So we said, every time I get a forecast, I select between 3 patterns. Don't worry about these patterns, they are just edge, cloud and fog. There are some scientific terminology I've used, forget about that. Right? So I just want to decide whether I have to use edge or cloud or fog. Imagine that I use something like, for example, edge, and it resulted in high energy and data traffic in my system. So I observe that this is not probably the best decision I should have taken. So I'll give a penalty for this, saying that, hey, you picked a wrong decision. So next time when you select it, you will ensure that you don't want to get a negative penalty, you try to select something better. Now how this works in principle is, when you don't have anything that you have to perform, you use a random selection. You just say, okay, let me randomly select something and perform it, right? Perform it and you get a feedback. So at least next time you know that maybe that is not the best action, right? So there is a mechanism called epsilon greedy strategy that is used here, which means that with a probability of 1 minus epsilon, you randomly explore. With a probability of epsilon, you select the best thing that has given us the highest reward. For example, if edge gave you the highest reward, you always favor towards edge. But you don't want that favoring to happen too much. So in order to do that, what you do is you randomly explore so that you also give fair chance to others. That's all the concept is, right? Yeah, so we did a self-adaptation approach. So there is also a tool, okay, this tool is not great, but still you can go and check it. What we do is there is an IoT system that constantly does everything, but in the plan part, what we introduced is we introduce a decision selector. I'll come to the verifier part, which will select a decision and I'm going to execute the decision, okay? So this is the change that we did. And now RL will decide whether you have to be in edge or fog or cloud. It's great. So AI is deciding everything. AI is forecasting, AI is deciding what needs to be done, but the problem is AI itself cannot be trusted, right? If you just use AI for everything, then the question is who is going to give you guarantee? Remember the third challenge. I said you need to provide assurance to the learning, right? So how do you provide assurance, correct? So that's when there are a lot of interesting articles on this, right? For example, Tesla, we were talking about Tesla, has this autopilot fix problem, right? I mean, autopilot problem where the car accidentally recognized something as a divider, it went and, it didn't recognize the divider, it went and crashed onto the divider and the person died. There are still, some investigations going on. AI was sending wrong people to jail. I was involved in some sense because the professor who was involved in this investigation was giving us a lecture during my PhD. So he said that at that point, a particular state in US decided that AI will decide if a person has to go to, is a criminal or not. So you just give the background information of the person. All the people belonging to a particular color were sent to jail. Doesn't matter. That's wrong, correct? So they stopped the system, correct? It was biased, yeah? And now AI camera operator was always, they tried an AI camera operator where the camera is controlled by the AI and it was covering a football match. Interestingly, after some point, they were only seeing everything through the referee's head, right? Because the ball and the bald head of the referee, right, looked very similar. So the AI mistook that the ball is actually the head of the referee and it was following that, right? So AI is great. It's a nice tool. It's a nice technique, but you also need to be mindful of where to use it and how to use it and when to use it, right? So we said, can we now add a verification process? So because I'm talking about a system, and the moment I talk about a critical system, for example, I cannot just allow AI to do everything as such. I need to have some kind of a guardrail or some mechanism by which I can be sure that this could be applied to the system. Because I'm talking about running software system, right? So they asked, what is the difference between a doctor and a mechanic, right? You know the story. They said, right, okay, doctor, they said, okay, I'm also doing the same thing, you're also doing the same thing. What is a big deal? So the doctor said, okay, mechanic, you are doing it, but you're doing it when the car is stopped. I am doing it when the person is living, right? When the life is happening, I'm operating on the person, right? Similarly here, when the system is running, you are adapting, right? So you have to be sure that the adaptation is correct. You don't want to just kill the system, right? Which could have adverse effect on other people who are using it as well. So how do you do that? We came up with multiple mechanisms. So we said, can we do something like this? So there is something called model checking. Again, how many of you have heard of model checking, model verification? No? Okay, forget if you have not heard it. Don't worry. I'll just try to simplify it. It's just a mechanism by which I can verify certain properties of the system by using a model. Okay, simply put, I'll create a model of the system. What is a model of the system? I'll say that, okay, there is edge node. So there is a node. So I'll represent this as circles, like edges, graphs, and so on. So I connect them. And I'll say, okay, now if I add this much traffic or this much of communication between the edge device, what will be the battery consumption? I can simulate it, essentially. right? So what I can do is I can create some kind of a representation of the system. I can simulate certain properties by saying what will be the expected energy consumption if this happens, what will be the traffic if this much happens. All that I can simulate, and based on that I can make a decision. Okay, now you might think, okay, what is the difference between this and machine learning? Here what we are trying to do is you are not essentially learning or anything, everything is static, more at design time. You have a representation of the system and you are just trying to simulate a load on the system, and you're just trying to quantify what will be the behavior in terms of energy consumption, data traffic, blah blah blah, right? Now the same thing I want to do for IoT system when it is running. So that was the key thing that we did. So we said whenever the system is running and I want to say, now I want to move to edge, what we will do is dynamically we will create a model of the system at that time. Based on the real-time status of the system, we will create a model of the system. We will apply it to the real system. We will say, okay, now if I move to edge, what will be the implication of the system? I'll check if I change to edge, if everything is going to be fine or not. If it is going to be fine, then I'll apply to the system. If it is not going to be fine, I'll forget it. Correct? So it's like, for example, consider that you have a nice 3D or thermocol version of your home, right? And you have your real house. And now you have to think that, okay, I want to break a particular wall. And you don't know whether it is going to work or not. So you have a nice thermocol, model of your house, where if you actually break a wall, it will give you the properties of the original house. For example, if you break a wall, it will all collapse, or it won't collapse. So it has encoded the same property. So if I test it here, I'll know if it is going to work. If it is going to work, I'll put it on the real system. The same thing we are trying to do here, right? So there is a running version, which is the model of the system, which has the qualities of the system. It captures every behavior of the system, and then it tries to do what it can be done. So we use something called probabilistic model checking. There is statistical model checking and probabilistic model checking. There is an entire literature by itself. I'm not going into that. So we use something called probabilistic model checking, where we specified properties like, I want my energy to be less than this, I want my traffic to be less than this, and now I want you to say whether the system is going to work or not. So this is the work we did, which is called quantitative verification aided machine learning. It's called quantitative because it's using probabilistic model checking. It will give you numbers in terms of how much will be the energy, how much will be the traffic. So every time machine learning or RL here comes up with a decision, you're going to create a model and you're going to check if this decision can be applied. What does this mean? It means that if I want to say I want to move to edge, what I'll do is I'll say, let me now move the entire system to edge, which means I'll create an edge model representation of the system. I'll check if this edge model representation of the system will satisfy my energy, traffic, or security, whatever requirements I have. If it satisfies, I say, okay, now switch to edge. So this is the whole, pipeline. So we did a lot of, of course, this is the more internal details. I'm not going into this, but we have this reinforcement learning, which will select the, gives the states and actions, and that states and actions will go to a model generator. Then we'll generate the model, we'll check the model. Then it will actually give a feedback to the RL. So there is a two-way feedback that happens. First, the RL will get a feedback from the verifier. The verifier will say whether the decision is good or not. If the decision is good, the RL, it is going to be executed. If it is bad, the RL will come up with a different decision. Now what we are essentially trying to do is we are trying to close the loop, converge RL faster. Because RL has an exploratory nature, it might take more time. So essentially because of the verifier, we are making a model-free RL kind of model-based, right? So that's the whole idea of what we attempt to do. Yeah, but of course feel free to read it. So, of course, I don't want to keep talking theoretical stuff. We actually did this, right? So there is a technical implementation view of this. So what we did is we took the real system. We have an instance implemented on the NDR. But for the research, what we did is we use simulator so that we can simulate more loads and stuff. So we use something called a cup carbon simulator. It's a very famous simulator. I think Gaurav, you would have used it, right? So yeah, it's a cup carbon simulator. So it can simulate, sensors. It can simulate communication between sensors. It will give you battery levels of sensors and all those information. This cup carbon simulator, that data is passed to a data streamer, which will, because it's real-time data, right? It needs to be streamed very quickly to the other side. So you take the data, you push it to a machine learning engine, which is our architecture view that I showed. So this is a technical view of the same architecture that I had showed, okay? The MAPE-K loop, but realized using technical stuff. You can see the same components here. You have a monitor, you have a batch machine learning engine, you have a real-time analysis and plan, you have an executor, so everything is here. Only thing that's get added is a presentation layer, okay? Because we want to visualize it to the people who are viewing it. So a batch machine learning engine will actually build a model, and this model is going to the real time where you have an Kafka. If you're interested in technology, what technology we used Apache Kafka, and this Kafka is streaming the data to a quality of service predictor, which is a model that is built using Keras. So it predicts the expected quality of service. And we have decision verifier. For verifier, the model checker, we use something called Prism, right? So Prism is a probabilistic model checking tool. If you understand the fundamentals, it's all based on Markov decision process. If you know MDP very well and probability very well, you can learn the tool. And it was all done in Google Cloud, right? So the whole thing was deployed in Google Cloud, and of course it was working. Yeah. So we did some experiments. I'm not going into the details. So we wanted to be sure that this is good. So we simulated the system for 30 days. We captured all the energy consumption. We wanted to see how good is the forecast. So to the extent, we did forecast using different algorithms, right? You tried naive, 3 algorithms. There is Holt-Winters, there is damped, there is SES, there is ARIMA, MLP, which is a multi-layer perception, and then you have our own LSTM. So we tried. So these are considered as the classical time series forecasting benchmark algorithm. So anytime you come up with a new algorithm, you have to benchmark against all of them. So we came benchmarked against all of them, and we observed that look at LSTM, it was having the lowest RMSE in multiple horizons. So you can forecast the quality of service for 10 minutes, for 15 minutes, even for 30 minutes, it was good, right? And we also want to do, so if you want to forecast, you have to, every time you want to forecast by looking at the previous X number of steps. So we wanted to see what is the good previous X number of steps. Because in research, you cannot randomly say, oh, I went with 5. What was the reason for 5? Or what was the reason for 10? So we tested that, right? So we said, what if I'll take the previous 5 steps to predict the next 5 steps? What if I take the previous 10 steps to predict the next 10 steps? So we used all these combinations, and we observed that it's better to use something like 10, right? So that was a horizon of 10 is always good. I mean, in this case, again, this is subject to the use case that you have, right? So then we wanted to see the energy and traffic. So first we tested with just reinforcement learning, right? So we have 3, which is edge, cloud, and fog. We observed that our approach was able to balance between them. So not very high energy, not very data traffic, so something in between, right? So this was the first study. Then we said, okay, but what if we add something on top of it, which is the verification. So can verification effectively improve your approach, right? We want to do it step by step. First we see what is good forecasting, then we check next thing, which is RLMC, what we call as reinforcement learning based model checking approach. Where in RLMC, what we observed is, we are getting a very high utility. So you can see that the RL approach is still bad compared to RLMC, because RLMC was much better than an RL approach, and we were able to achieve a high utility, where utility is defined by a combination of energy and traffic, very similar to SWIM, how SWIM did it. You cannot just use a model checking also. One is it takes significant amount of time, right? So for example, model checking itself can be used. So what is the significance of this work that we did is, previously people used to do model checking. They don't use RL. But the problem with model checking is, imagine that a robot is moving and it is stuck at a point and it has to adapt. Okay, its camera is gone. Now it needs to decide whether it has to use a LiDAR, it has to use something else. The problem is, it has so much of state space, so much of actions that it can take. What model checking does essentially is, it will take each action, apply to the system and say whether it is good. So by the time it exhausts like 100 actions or 10 actions, it will take a lot of time. But with RL, what we are saying is, we'll give you one action. You just tell whether that action is good or not. Maybe RL will go to a stage where it is giving multiple actions, but still at some point you are going to improve. But if you just use model checking, it will have a big impact. So even in our results, when we use model checking, the time taken for model checking to come up with a decision is close to 4 seconds, 5 seconds. But with RLMC, it's close to less than 1 second, right? So that's the difference that we are talking about. So this is the plot that you would be interested in, right? So when we use a combination, initially, whenever RL gives a decision, most of the time it was wrong. So it was corrected by, it went up to 6 corrections where there was a back and forth of interaction. RL will give something, verifier will say wrong. Again, RL will say something, verifier will say wrong. So there will be back and forth. But after some time, this correction completely reduced. So you can see the scatter plot where initially there is more corrections, but as time progresses, it is very less, right? Also the growth, right? Initially, RL takes some time to improve, but as it improves, you can see the rate of improvement is much higher compared to other approaches, right? So these are some of the observations you have from this. So essentially, model checking allows reinforcement learning to converge faster, which was a big result. of my PhD itself, because we didn't expect that it will be a result like that when we started the research. But it went on. This paper was a best paper candidate in one of the best conferences in software architecture. Yeah, so this is the efficiency part, which talks about, RLMC on average takes 2 seconds, RL takes around 0.1. Okay, but we didn't want to, stop there. I'll just quickly go through some of this because these are more generalization. Whatever I wanted to convey was already there, but we didn't want to just say that it is all applicable to IoT, because one of the groundbreaking results we had, as I said, was the combination that RL and model checking can work. This was one of the first works that talked about the fact that you can use a combination. But to use reinforcement learning and model checking in every situation is very hard. It may not work very well. So we said maybe we'll tone it down. We won't use model checking, but at least with RL, how much can we do adaptation, right? So we wanted to talk about the scalability. We also wanted to see if it could be generalized. So we took a very interesting domain. Do you know what this image is? Any idea? No. Interactions between what? No, you are not supposed to say. Interactions between what? User and no. It's interaction, but not between user and server. So I talked about microservice in the beginning, right, where you can break down systems into small services. These are the number of, each of these are the small text that I cannot even see. They are all different microservices that are there in the system, right? And this whatever you see as blue is the interaction between the microservices. So it's interaction, but between the services. Which, what I'm trying to say is all these companies, they adopted microservice architecture. One of the biggest drivers is Netflix. If you are interested in software engineering or engineering in general, system engineering in general, you should read Netflix engineering blogs. One of the best, right? So what they did is they built this system, huge massive systems of so many thousands of microservices, and each service is replicated to multiple instances so that you don't have problems with availability, security threats, and so on. Even if one goes down, something else is going to come back. And they are all deployed across geographical regions. So a same service, for example, if you want to authenticate into Amazon, if you are using from Surathkal, you might be connected to Mumbai AWS server. But the same service is also available in European region. It is also available in US region. Same authentication. Depending on where you use it, usually changes where it is routed to. So, but one of the challenges in microservices is this communication challenge, right? So if one service wants to communicate with another service, it does not know which instance it should use to, right? For example, there is a service A, it wants to communicate to service B. Since I said that services are replicated across geographical regions, they are duplicated, replicated, and so on. So how do you know which service instance you should talk to? Because there are multiple services which provide the same functionality, implemented in the same way but deployed in different places, correct? So which will you choose? So this is a problem which is addressed through something called service discovery, right? So, this is a very classical stuff in microservice or service-oriented architecture. There is something called service discovery, where there is two types of service discovery. One is client-side service discovery and another is server-side service discovery, right? So in client-side service discovery, what happens is every services will register to something called a service registry. So there is a service registry where every instance will say, hey, I am this person, I am located at this location, this is my response time, or some parameters. Similarly, every service will register. So in client side, what happens is the service instance is a registry aware client, which means the client knows where the registry is located. It will go and ask the registry will say, these are the bunch of instances you have at your disposal, you can decide which you want to pick. So the client has the responsibility of using an algorithm to decide which service it should connect to. Okay? In the server-side service discovery, very interesting thing happens. So in server-side service discovery also, everyone registers, but the client does not have any responsibility. The client will say, hey, I want to talk to B. And this person's responsibility is route it to a particular instance of B. So it uses an additional component called a router. Now this router is now put into a load balancer and so on in a modern architecture, but I'm just trying to give you a separation, right? So this is a process, but what we wanted to investigate the same lines of self-adaptation is guarantee that whenever I select an instance, it's the best performing instance. When we did a check, this is not always. So if I communicate from here to AWS, it's not always guaranteed that AWS is going to probably it is going to provide me the closest one, but there is no guarantee on the fastest one. So how do we go about solving it, right? So we apply the same approach. So we took a real kind of a system. It's called Sock Shop. It's a e-commerce system for buying socks. It's a toy example. Not a toy example. It's actually a very complex system, to be honest. It has a bunch of microservices, and there is a client, and the client will now communicate to a payment service. Which of the payment service you will pick in such a way that you will optimize the response time and energy balance between them, right? When I say energy, depending on which service you use, right? Which region you are located. Like for example, India, Mumbai is powered by fossil fuel. So the service instance is going to consume more energy in terms of energy consumption. But if I am selecting something from European region, which is powered by solar, for instance, it's more green powered essentially. That's the more or less the idea. So we said, can we now introduce a machine learning based MAPK loop with a service registry, so that can we apply the same principle? We monitor, we use a combination of forecast and RL to decide which instance to connect to, right? So this is what we did. So this was published again in multiple venues. So again, we use a similar approach. Whenever you receive a query saying that I want to connect to a particular service, we identify the set of instances. That's a traditional service discovery process. To that, what we do is you forecast the expected quality of service. It could be throughput, it could be energy, it could be response time. You forecast that, and we create a ranking, and then we use RL to select, what would be the optimal instance that you want to select. Yeah, this was published again in multiple venues in different ways. One, we focus only on response time, but this paper that you see is ML-enabled service discovery. We use a combination of response time and energy consumption, right? Yeah, so you see so traditionally you can use approaches like round robin. You switch between different services and you say, okay, for now I'll select a service 1, now I'll select service 2, like that you switch. Or you could use the Q learning that I was talking about, right? So we used a reinforcement learning based approach, and we could notice that RL was significantly performing better with the combination of the time series forecasting using LSTMs, right? So that's the bottom line. We wanted to extend it further. I'm not going to take too much time here, but what we did is we said, you have microservice system, it is working. It is working in IoT systems, but most of the systems today are microservice based IoT systems in IoT, in smart city environments, right? So if you want to, for example, imagine that you are in a city like Paris, or imagine that you are in Mangalore, and imagine that Mangalore is a smart city, which means that there are so much of sensors that is talking about vehicle movements, in air quality, water quality, everything, and so on. Now today, in most of these modern cities, if you go and you say that, hey, I'm here for 3 hours, 4 hours, and you want to navigate that place, you will say, okay, for train, use this application. For bus, use this application. For restaurants, use this application. You have to, essentially use a bunch of applications, right? But they're all powered by similar backends. So what we thought was, if we have a, system like that, where it's all API-based system, and there are a bunch of IoT devices that are powering data, what if we could dynamically build application based on what the user wants? The user comes to Mangalore and says, hey, I'm here for 3 hours. I would like to visit, do a quick visit of Mangalore, and these are my preferences. I'll build an application that contains all the information that you need for your time of 3 hours, rather than asking you to download all different applications, right? So, but at the same time, I'm mindful. The application I selected, I optimize the response time, I optimize the throughput, so that I select the services which is guaranteeing you the best response time. So that in this way I can also deactivate some IoT devices. One of the problem in IoT devices, if you have worked with IoT sensors, it keeps sending data every 3 seconds, 10 seconds, just like that. Sometimes you don't need that much data, right? So can you switch off that data? Say that I don't need the data. Now in this way you can also save battery powers of sensors. You can also improve their lifetime. So this is, again, going back to our NDR, since you already know NDR system. Our idea was, imagine the NDR case itself, you have all these IoT devices as I explained, you have these different services. Now based on what the user wants, can I just build that as one single application? So if the user says, I want to check availability and just check weather or do something, I will create an application that will be just a combination of 1, 2, and 3 services, rather than going through all services, right? Yeah, this is called multi-level adaptation, because there are adaptations happening at multiple levels. The user will say something based on that we pick the services. So there is an adaptation at the user level, there is an adaptation at service level, there is an adaptation at IoT level. So it's essentially the combination of what we have been discussing so far. Yeah. So this is the architecture of the whole approach itself. This is too much to explain now, so I don't want to go too much through this. But essentially the idea is, on one side, you have this edge nodes, which is your IoT devices. You have the fog, where you have the basic compute, and you have the cloud, right? So all the microservices data is constantly monitored. We are monitoring the data of the fog itself. So all the quality of service data is monitored. Now what we do is, every time the user says, hey, I want these functionalities, there will be a goal parser that will understand what is the goal of the user. Based on the goal, it will identify the corresponding services. Based on the services, it will decide what IoT devices needs to be activated and not activated and so on. Again, this resulted in a couple of publications. So essentially the tech stack behind this is very complex, right? As you can see, this was actually implemented. So we use something like C-Advisor, Container Advisor, which will give you the metrics of containers when they are running. It's all implemented in Docker and Kubernetes. We use something called Istio, which is a service mesh, if you have heard of it. So essentially Istio, service mesh is like a low-level infrastructure layer attached to every microservice. It will even tell you, you can even change security policies. So if you are using a service, you know that there is an intrusion, you have detected an intrusion, you want to change the security policy, you can dynamically change through Istio, right? So it provides all this functionality. So essentially it was a way by which we could interact with the service in real time, right? So that's what we did. Yeah, of course, I don't want, so there is a nice repository for this. Feel free to scan this. You can go and check the implementation yourself. We have a very dummy implementation of this where we have actually implemented it. I hope the QR works, yeah? You're scanning, okay, yeah. So there is a utility, overall utility and energy consumption. We were able to observe that with our approach, which is a dynamic adaptation, we were able to, achieve a very high utility in terms of, energy of the IoT devices, response time of microservices and so on. So essentially what we did, right, we moved the concept from self-adaptation to self-learning, right? So we said, if you have an architecture of a system and the system is running, can I dynamically adapt the architecture, validate if that is the correct adaptation, deploy the system, monitor what is happening in the system, and keep doing this feedback. I mean, keep continuously doing this of, adapting, learning, monitoring, and so on. So essentially, in this way, what we are essentially saying is you can move from self-adaptive architectures to self-learning architecture, right? So this is the whole idea of what we did, and that's essentially summing up my PhD, but that's what we did. And we also extended this to something called the human-computer interaction, HCI domain. So it's like, can we, because now this can be applied to many things, right? Can I check the user's emotion and dynamically adapt the user interface, right? Whether they are happy, I'll use a light interface. If they are sad, maybe I'll use a dark interface. I'll keep changing, but in a way that I also want to optimize the battery power. Dark mode will actually save more battery power versus light modes and so on. So again, we use a combination of RL here, right? We use reinforcement learning to, you get the face detection, you identify the emotion, we use RL to decide which interface to use. And we studied with users. So in Denmark, people actually use this, 45 users use this, and they gave us a feedback, and based on that, we came up with some results. Again, from a publication side, we had some journals on this, but that is there. But I'll just quickly show you something because I thought this would be interesting at the end. So we didn't want to stop there, right? Making AI real, we said, what can be done with all this AI in a real life, right? So we have the Smart City Living Lab in our campus. Gaurav has visited. If you have not been there, please feel free to come at some point, let us know, we'll be happy to host you. Live test Smart City systems in India, it's with a partnership with the Government of India through Ministry of Electronics Information Technology and EBTC, European Business Technology Council. So we have a Smart City Living Lab, which is like a test bed for any smart city solution. We have 400 plus IoT devices deployed across the campus in different verticals in terms of solar monitoring, energy monitoring, water quality, water quantity, crowd monitoring. I can just go on with the list, right? So all this are being monitored, and based on this, you can do different things. So some of this concept, not all of this, right? I mean, this is the reference stack, right? So you have, and interestingly, you have devices sending data in different communication protocol. You have LoRa's, you have Zigbee's, you have Wi-Fi, you have Wi-Fi's, you have 4G, 5G, all these different modes of communication protocol. We have an interoperability layer that takes the data from all this. We use something called OM2M, which is a software that follows the 1M2M standard, which is a standard recommended by the Department of Telecommunication as well as by multiple standards across the world. So yeah, this is the high level overview. So we have 350, now it has reached 400 sensors as per the latest update. Yeah. So what we did is we built so this is the Living Lab in action. You can go to the website and you can see this in real time, okay? You can just go now and you can actually check this dashboard is live. It actually shows the live dashboard of all the different sensors in our campus. This is a map of IIIT Hyderabad. These are all the sensors. We also have sensors outside IIIT Hyderabad in Gachibowli, measuring the air quality and so on. So what we did is we took inspirations from this and we applied to a simple domain, right? Some of these idea of adaptation to a simple domain of water. Because in water, some of the challenges exist in terms of maintaining the infrastructure, water will leak, the pipelines will leak, right? And the network itself is very complex. So we said, can we do this kind of adaptation in a smaller network? I mean, because we didn't want to start off in the entire smart city, right? So we wanted to start off somewhere. So we built something called as a digital twin. How many of you have heard of digital twin? Very less. Okay, the idea is, can I create very similar to what we discussed so far, can I create a virtual replica of the system? Okay, so there is a virtual replica of the system, there is a real system. Okay, now whatever happens in the real system also happens in the virtual system. Whatever change I do in the virtual system, and if I approve it, it gets applied to the real system. So there is an actuation. So you can see a MAPE loop here, right? I can constantly monitor, I'll get all the data to the virtual system, and whenever I want to change something, I can change there and can actually come back. The interesting thing the virtual system also provides is I can also simulate things that doesn't even exist. For example, in a water quality scenario, right? I have this, so we took this map of our deployment, right? This is the real deployment. So we have a pump house in IIIT, right? And this water goes into the overhead tank. From that overhead tank, it goes to an RO plant, it goes to an RO cooler. So this is a real pipeline we have in IIIT Hyderabad, and we have sensors in all this. We have water quality, water quantity sensors, measures the turbidity, amount of pH levels, right? How much of water is flowing. So all this is monitored. Now we said, what if we add the impurity, this much impurity, how will it change the behavior? Or what if this is the impurity, what would have impacted it? How do you test all this? You cannot really put the impurity on the real water and say, okay, now my water is contaminated, because people are actually drinking it, right? So this is where a digital twin can help. What if I turn on something? What if a pipe leaks? How much water will be lost? So I want to test all this what if scenarios, right? So this is where digital twins can help, and based on that, can I actuate my pump in a particular force, my motor in a particular force, right? Can I actuate based on that? Based on that, can I control the flow of water? So all these decisions you can make. So we created a digital twin. I'm not going into the architecture. It's very similar again to the, somehow the MAPE loop, right? Because here also we collect all the data in something like a knowledge. You have a digital twin layer which has multiple things, so it can simulate. It has a model repository where it has AI models as well as data models of the system, and based on situations, it will trigger back to the real system itself. So this is the digital twin for water network. We have a real twin. I wanted to show the demo, but unfortunately, maybe we'll do it in a later offline setup. I'll put out the video somewhere so that you can check it. So here the interesting thing is, on one side you have this water quality digital twin. This is the real view of the system. What is happening in the real system? This is a simulator view where you can simulate. So you can say, hey, I want to add, for example, soil impurity in particular grams. I want to see how much it will affect the quality of the water. I can do all the simulation here. And then I have a nice visualization which will show more detailed visualization of what is happening in the system in terms of flow and so on. So this work, I think part of this Gaurav was also part initially of this work. It was done in collaboration with a company called ZF Tech. They're one of the largest companies. It's a German company. So this was part of their CSR work. But now we are expanding this to air quality. We are also building this for other domains. Now what I said is, I wanted to show, this is the demo part, but it won't play anyway. But what I wanted to say is, I wanted to just give a glimpse into the reality, where it's not just a self-adaptation in the air, you can actually do it in reality, and we have implemented it, right? Now the final thing is, we talked about AI, using AI for self-adaptation, but what about AI systems themselves, right? It's not just using AI for self-adaptation, but what about systems that use AI also? Can we do self-adaptation of that, right? So very quick example here. If you take object detection as an example, everyone relates to object detection, right? So you have multiple models that I can use for object detection, right? You could use a Detectron, MobileNet, YOLO-based models, and each model has different, properties in terms of precisions, in terms of response time, in terms of cost, everything, right? And not every time you need the same model. For example, if I put a camera here and I want to count the number of people in this room, I need a very heavy model probably because the number of people are a little dense. But imagine only one person. I was sitting before the session was starting. Sir allowed me to sit here for a meeting, right? So it's only me that is sitting. I don't need a complex model that needs to be run there. So based on the context, can I dynamically decide which model needs to be run in a particular time? In this way, I can save, of course, power, but I can be more faster. If it is a light model, it would be much faster in terms of detection. I can save cost and so on, right? So idea is, what if we could switch between machine learning models? What we call is as machine learning model balancer. This was a work that came out from one of my MS by research students and an undergraduate researcher. So where we said, again, the same concept of self-adaptation, but here we are doing it for machine learning systems, okay? Oops, yeah. So we didn't want to stop. So the idea is we decide when to use which model. We are not using RL yet here. We are using simple approach here, right? We are just using a simple epsilon greedy based approach. Initial approach was using an unsupervised learning. I don't want to go into it. But later we decided to use a simple epsilon greedy based approach. So with a probability epsilon, you randomly select a model. With probability 1 minus epsilon, you select it based on the previous performance. Right? So this is a tool. You can actually go to this website. This tool was also published. This tool allows you to check scenarios where you can come up with your own algorithm to switch between ML models, particularly for object detection. We have recently extended this to LLMs as well, but I'm not touching LLMs yet. I'll wait for Rudro's session and then we'll go into the generative AI side of it, right? So you can scan and you can see the repository of the tool. You have a nice website. There is also a video tutorial demo on how to use this tool and how to build on top of this. So we extended this further to also something called EcoMLS, which is, now you are talking about machine learning system, but if you know, since I also come from sustainability background, it's very important to understand that AI is one of the killers of environment. I might be killed for saying this here, but it's actually true, right? The amount of data centers you have and the amount of number of carbon that is being emitted because you are using AI is crazy, right? To the extent today, software's emissions is equivalent to air, rail, and shipping combined. That's the estimation that has been made, right? Just by running softwares. So if I say the best way to contribute to environment is go and stop streaming in Netflix, none of us will agree for that, right? Because Netflix itself consumes energy that can power 45,000 households in the US as per stat. 45,000 households, right? So the data center. When I say Netflix, it's actually the data center because that's what runs Netflix, right? And the water that is required to cool the data center. If you have to be mindful about environment, it's now, right? When we build softwares, can you be more mindful? So this is one fundamental thing that we have in our research group as well. That's our research group is called SA4S, right? So the whole idea is how do you contribute towards sustainability? So here, this approach actually helps you to also reduce the carbon footprint of AI models because you decide when to use a heavy model versus when to use a light model, right? So that's what this was about. It's called balancing between energy and performance. We published this in something called Greens. It's a very nice workshop co-located with a top tier conference. If you are interested, feel free to submit for next Greens, right? It will be great to receive some of your submissions. Yeah. So this is the work where we just extended the self-adaptation to AI systems as well, right? And I'm not spending too much time. I also know that I'll be out of time now. But this also we moved to Edge, where we actually deployed it at the level of Edge also, right? We are working with Qualcomm company, and we developed this approach called Edge ML Balancer. So same idea of switching between AI models, but can you do at the edge? Why you can do it? Why you should do at the edge? What is the benefit if I do at the edge? Faster, and then there is even more bigger thing. Cost or rather battery. Yes, data security definitely, yes. Right? So we could switch between different AI models. We actually showed to Qualcomm that how much battery we could save if you decide when to use what, but at the same time without compromising accuracy. Because as I said, most of the time you don't need it, right? That's the point. It's not that you're just, yeah. Yes. I was expecting someone to ask that question. Thank you so much for asking that question. So yes, definitely Edge is a constrained, a network. So where we are talking here, we are talking about light models in Edge. Even light models have comparison. But in order to tackle that challenge, what we have done is we have moved from Edge to say something like Edge Cloud Continuum. So you don't want to be just limited by Edge, right? There could be nodes, whenever you decide, you can have models that are running on the edge and they are only on the edge. But sometimes you might need more power, as you said, because my context is different. I understand that edge cannot be able to handle it. We immediately move to cloud. So there is a switch between the edge cloud, and even in cloud, you decide which model to use. Yeah, that is a trade-off you have to pay, right? Some trade-off you'll have to pay, right? It's best. See, you have to look at it this way, right? The whole point of self-adaptation here is it's not about whether this is right or that is right. It's about how do I balance between the trade-offs. Yes, I will pay latency, but on the other hand, what am I getting? I'm only paying latency only for certain instances, not for the whole time. Correct? Because eventually, what is the benefit that I'm getting? That's the point. It's not about that instant of time. Maybe at that instant of time, because thanks for this question, when you look at sustainability, it's a long-term property. You cannot say that I reduce energy consumption now, because of that I'm great. That's not the case. It's about, can I ensure that over time, my energy consumption is minimized? So there might be times I might go up, there might be times I might go down, but eventually my system is in a steady state, right? And that is okay, because there could be a peak situation where you'll have to use cloud. You cannot say, as I said, you cannot say that don't use the cloud itself. That's like saying, okay, don't use the system. But can you balance it out? Right? Definitely a problem. So in critical applications, you try to, I mean, if the security, privacy and all are concerned, you try to put it in the edge itself. You don't primarily go to the device. And today, to be very fair and honest to you, most of the edge devices, like we have tested across multiple phones, even NVIDIA Jetsons. You are talking about Raspberry Pi 4, yes, a problem. But this NVIDIA Jetson can host crazy amount of YOLO M models, right? Yeah, and even Qualcomm, that edge, I mean, if you take a Samsung Galaxy phone, it has probably 54 machine learning models that are deployed on your pocket, right? And we are talking edge is limiting. Edge has crazy amount of compute today. They are very good, they have NPUs, they have GPUs, they have all different combinations of processing units that are managing, but still there is a limitation. But my point is, most of it, you can use light models itself and your problem is solved. And you are not going to use edge for every scenario. You can also think edge node as a laptop. So when Rudro shows a demo today, we will show about a generative AI case where eventually we can run it on an edge because of privacy as one of the concern, right? Yes, security as one of the concern, you can run it on edge. But there we are toning down the model, right? Because when you want to use it for a very specific domain, you don't have to put the entire YOLO. You can custom train a model, right? And you can custom train a neural network in such a way that you only need probably 50, 70 layers. You don't need all the million layers. It's not needed. So sometimes we overdo. What we do is we take a cloud model and we adapt it to edge. That doesn't work. If you want to build for edge, you have to build it for edge. And that's where the whole challenge is. So when we think, what we are thinking is we are force fitting a cloud to edge, which probably won't work. That's it. So just want to say, if you have not been listening to all this, what this guy has been talking about, if you just want quick takeaways from this session, all I want to say is this, right? Self-adaptation can be used as a mechanism to handle runtime uncertainty, right? As we were just discussing, you can, you have this kind of discussions with the architects and say, okay, some of this you cannot decide at design time. You have to go at runtime. So in runtime, there could be many situations. Now, how do you handle such situations? So definitely this could be a way. Machine learning plays definitely a big role in enhancing self-adaptation. Now it's a proven thing in terms of a lot of work that has come out that definitely it helps, but a lot of challenges still exist, yeah. As I said, more work needs to be done for generalizability, scalability, and machine learning system itself requires a lot of attention because everyone talks about using AI, using AI, using AI. But what about AI system itself? Are you retraining your models periodically? What about model drift? What about data drift? Do you have an MLOps pipeline? All this are big challenges that many times we don't talk about. Trustworthy of AI model, security of AI model itself, data poisoning attack, model poisoning attacks. You have so many things that you have to discuss about in machine learning system. Not about just using AI. AI for security is great, but what about security of AI itself? Those are, I think, big questions that we need to discuss about. So we did a DuxTool seminar in this topic on software architecture and machine learning 2 years back at DuxTool in Germany. So we came up with a very nice report that lists out some of the challenges that community needs to evaluate in terms of using architecting AI systems or using ML for software systems. So yeah, AI is here to support, not to replace. And the big question that you might be asking is, I talked about a lot about AI, RL, DL, but I didn't talk about generative AI. So how can generative AI help in this whole process is something we will discuss in the post-afternoon session. We'll start off with a tutorial by Rudro, who's my PhD student, who will provide some basics into some of the techniques and so on. With that knowledge, it will help you to understand better the second part where we will talk about how generative AI can be leveraged. Yeah, thank you.
Okay, so we'll break for lunch. That's is here with us for 2 more sessions. If you have any doubt, any question, you can.
Yeah, I'll be happy to answer. Anytime, if yeah.
Self-adaptation is
Yes.
adaptable to other water distribution networks which are already in place in Hyderabad.